Okay, so let's look at the problem together. So this problem is about a company that has two different kind of recycling processes that transform those different paper products into three different types of pulp. Okay, and so the paper products include newspaper, mixed paper, white office paper, and cardboard. These different paper products get to go through two different steps in this two recycling process. And in the first step, they will be recycled into just the paper pulp. Okay, and each different types of paper material have different yield in the two different recycling processes. Okay, so for example, each ton of newspaper that goes through the first step of this recycling process 1 will have 0.9 ton of paper pulp as the yield. And then those general paper pulp will go through this second process, so this other operation, to be transformed into pulp for more specific purpose, which will be the newsprint, packaging, and printing paper, and the print stock pulp. Okay, and the cost per ton is different for the two steps in the different process, and the yield rates are also different. So why we say this is a generalized network problem? As mentioned earlier, generalized problem is the one that loss or gains will happen during the transition process. Okay, and in this case, we'll have loss because of the yield rate. So for each ton of newspaper that goes through the first step of the recycling process 1, 0.1 ton will be lost because the yield rate being 90%. Okay, and when it goes to the second step, the newspaper pulp, the paper pulp, when it goes to the second step, there will be different yield associated with it. And this is the first problem that at the first sight, it does not look like a network problem. Okay. And at the beginning, we said there are a number of business problems that we can translate them into a network problem. And you will find that once the network is drawn, like it, and once this paper, once this problem is represented by that network, the modeling part is really easy. But it's the part that formulates this, understand this problem, and create this network graphic representation for this problem is the challenging part. Okay, so let's see how do we translate this problem into a network problem. So let's just take this newspaper as an example to do the analysis. Okay, so we know that this newspaper, when it goes, let's just see, okay, when it goes to process 1, it goes to recycling process 1. It will have a yield of 90%. Okay, so when it goes out, you will have to multiply this 90%. Then, after this first step, you will get some general paper pulp. Okay, and this general paper pulp, so I'll put here you get paper pulp. And when those paper pulp goes from recycling process 1, the first step, to the second step, it may yield into 3 different specific paper pulp. Okay, one is newsprint. Okay, I'll just put newsprint pulp. And here you only get 95%. You can also get packaging paper pulp, which will give you 90%. And you can get print stock. Okay, print stock pulp. This one you get 90% yield rate. Okay, so this is for the newspaper to go through this recycling process one. At first, when it comes out from this first step, it lost 10%. Okay, and when it got translated into these three different specific pulp type, it will lose a different percentage. Okay, and if it goes to recycling process 2, what happens here? it will have a yield rate which is 85%. Okay, and what comes out from this first step of recycling process 2? Paper pulp, right? The general paper pulp, which is the same here. Okay, and these general paper pulp will be transformed into these three different specific pulp again. And since it's process 2, they have different rate. Okay, so let me just use a different color. Okay, so here it also goes to newsprint, packaging paper, and print stock. And the yield rate, what we need to read from this second table, is 90%, 95%, and 95%. You can see that the second process, first step is pretty inefficient, but the second step is pretty efficient. Okay, so that's only for the newspaper. It goes through the two separate recycling process. And we can do the same for the mixed paper, white office paper, and cardboard using the same destination points and the transshipment nodes. Okay, so we can put back. So we'll have the mixed paper, white office paper, and cardboard, and they will all go through the same process. And moving this yield rate to the arc. Okay, oops. Moving this yield to the arc, we can create a network that looks like this. Okay, so we have the newspaper, mixed paper, white office paper, cardboard being the supply nodes. Okay, and they all go through these two recycling process 1 and 2. And these first groups of arcs represent the first step in both process. And these second groups of arcs represent the second step in both recycling process. Okay, and at each step, there will be a yield rate associated with each arc. Okay, and then we know from the problem statement, we have 70 tons of newspaper, 50 tons of mixed paper, 30 tons of white office paper, and 40 tons of cardboard. And also, now let's go back a little bit. And also, she has a contract to produce 60 tons of newsprint, 40 tons of packaging, and 50 tons of print pulp. Okay, so that these represent the demand. So we put the demand here, and the transshipment node has both have 0 demand because we don't want any paper pump to just stop here. We want them to be transformed into those specific type of pump. Okay, so with this analysis, we can see the problem get translated into a network problem. Okay, with supply nodes, demand nodes, and transshipment nodes. Also, it's similar to the problem we covered earlier. It's a minimum cost network problem because we have those costs associated with each step of these two recycling process. And what we want to do is to minimize the total cost in this entire recycling process. Okay. And our decision is to determine how many tons of the newspaper, mixed paper, white office paper, cardboard to to send to the first step of each recycling process. Okay, and it should be noted that because the yield from both recycling node from the first step is general purpose paper pulp, and say even the paper pump that got from here, we can send them to be the different specific pump. Okay, so it's only like the cost that matters. So what we can do now is to, oh sorry, I forgot to define the decision variables. Okay, so our decision variable will be xij represents xij to represent so here on this side it's tons of paper to send from. Okay, so I'll say tons of paper material or pulp, because we're talking about this part too. That part is that part is this part is pumps. Okay, so this part we're talking about paper material, and at this part we're talking about paper pulp. Okay, and here I'm going to use sent from node I to node J. We're not going to say transport it, okay, because we know that some loss happens along the way, and our xij only represents the starting volume. Okay, so when we know that when xij gets into this point, it will just be 0.9 times xij. Okay, because that's the actual volume that you can get out from this first step. So after this first step, we know loss happened all the way, and when the 5 tons of newspaper material get finished from this first step and it reached to this node 5, it only has 0.9 times xij times x15 tons left. Okay, so just say sent, meaning that represents the starting volume here. This many was sent, and when this volume get to transported to here, only 90% of them are left. Same on this side here. Okay, so here I again emphasize clear and accurate definition of your decision variables. Okay, so here is one example. Our xij will use the special word sent to make sure it actually captures what we meant. Okay, so that's the decision variables. And then our objective function will be pretty easy. Just minimize the total cost. So you take the sum product of all our decision variables and the cost that are associated on this network being provided in those tables. Okay. Then let's look at the constraints. Okay. Since this is a network problem, a transshipment problem, let's see. Remember when we write the constraint for any transshipment problem, first thing we do is to check the relationship between the total supply and total demand. So in this case, the total demand is 150. And in this case, 120. That's 190. Right? Okay. So just by looking at these two values, we know that we have enough supply to meet the demand. Okay. However, if you think about what happens on the way, okay, we're saying in those generalized network problem, loss happens on the way. So when this 190 tons of total supply get to the point of their destinations, we don't know whether we still have 100. For sure, we know that for sure we no longer have 190 tons. Okay, and we don't know how many are left. One thing we can do is that to see, okay, if we use the total supply multiply the minimum yield here, okay, which is this one, multiply this 75%, and multiply this second minimum yield rate, which is 90%. If this value is still greater than 150, then we know, okay, even though we know loss will happen along this path network, we are sure that at the minimum yield rate, we're still able to meet our demand. Then we know exactly what the actual supply and the demand relationship is. However, in this case, it's not. Okay, but we're not sure whether it's going to meet it or not. So what we can do is to assume that the total supply will meet the total demand. Okay, and formulate the constraint according to this assumption. And then we implement it in solver, try to solve it. If solver cannot find an optimal solution, or actually more accurately, if solver cannot find a feasible solution, then that means our supply is not going to meet the demand. Then you change the sign of your constraints, solve it again. Then you know, okay, then you will be able to find a solution. Okay, so for this problem, since we're not able to make sure that we're not able to make sure whether our total supply is going to meet the demand or not, then what we're going to do is to assume it will meet. So subject to, so for all the supply node 1, remember the constraint format, okay, inflows, so no inflows for all of those nodes here, okay, minus outflows, x15, x16, greater than equal to, because we are going to assume we have enough to meet the demand. Okay, so greater than equal to the supply there, negative 70. Okay, so same for node 2, 3, 4, x25 greater than equal to this, x35. Okay, so these are the supply nodes. And for the transshipment node. For node 5. Okay, so what are the inflows? Inflows include the flow that goes from node 1, 2, 3, 4 to node 5, right? So x1, sorry, 1, 5, x1, 2, 5, x3, sorry, 3, 5, and x4, 5. Okay, are those the true inflows? In another word, are those the actual amount that goes into node 5? Remember, there is a yield rate, which means the loss has happened when those volumes were sent from the 4 nodes to this node 5. And when they actually reached into node 5, those loss has already happened. Okay, so the actual inflow to node 5 should be 90% times this one plus the 80% times x25 plus the 95% times x35 and the 75% times x45. Okay, so these are the true inflows to node 5. Then subtract the outflows from node 5. And since we defined the decision variables to be the amount sent out from those nodes, so x57, x58, and x59, these are the true outflows. So these are the amount sent out from this node 5. You don't need to multiply the yield rate because the loss has not happened when they are sent out. Okay, so inflow minus outflows should be greater than or equal to the demand there, which is 0. Okay, then you can write the same thing for node 6 and post your solution in the following forum. Just post the constraint that you write for your node 6.